design team. I call them the Super Tiber design team. Because they're really doing two projects for the price of one, effectively. One is a liquid rocket engine and a test cell. Testing. So I'm going to hand over to you.
All right, good morning. My name is Rachel Rise. I'm the design team lead for Tiber Designs. I have here with me today Ahmad Bahita, Lucas Widener, Daniel Dick, Robert Myers, and Shubha Chanpuria. You'll also be hearing from Cameron Kurtz, who has been working remotely with us this semester and has embedded audio clips within our presentation to address possible connectivity issues that we might have experienced in this building today. So, and then he'll be joining us for Q&A. This semester, we have completed preliminary design work for two separate but related systems, a liquid rocket engine and its accompanying test cell. I will briefly introduce both, and then I'll introduce the team to discuss the design solution for each. Our project comes from the Eagle Aerospace Amateur Rocketry Club here at Embry-Riddle. They are entering the FAR Mars competition, which is a collegiate competition to send a 1 kilogram payload to 45,000 feet using only liquid propellants and passive fin stabilization. Eagle Aerospace has commissioned Tiber Designs to develop the engine to be used in the flight vehicle. This engine bears the name Janus. Though Janus is not the first liquid rocket engine to be developed at Embry-Riddle, it is the first that will be tested in a new test cell that meets all of the needs of the liquids rocket program. There's a long-standing need for such a test cell on campus. Though there are existing facilities, they lack the necessary supporting equipment to fully support liquid rocket testing and their capability. This is because liquid rockets require much more permanent installation of supporting equipment and infrastructure. For example, test cell 1 doesn't have a good space to store a lot of equipment long term and protect them from the weather. So if teams wanted to test in test cell 1, they need to design their entire system and set it up and take it down every time they need to test, wasting time in redesign for a system that should already be there. It also poses a safety hazard because there is no place to store propellant tanks, which is especially a concern when handling materials such as liquid oxygen. Test cell 2 was developed to meet part of the liquids program need. You can see there's a small, maybe if I can get my pointer to work. There's a small space for propellant tank storage, but it still leaves equipment exposed to the elements and runs the risk of damage over time. To fully support liquid rocket testing in its full capability, we need an enclosed and secure testing facility with permanent equipment. Test cell 3 is our solution to this need. It features an interior thrust takeout system and propellant feed system that fully support liquid rocket testing efforts with up to 3,000 pounds of thrust output, so it can support projects well into the future. It also features modular instrumentation, so that teams can swap out the sensors and take the measurements they need for their individual tests. Finally, test cell 3 features enclosed and secure storage space and on-site tooling, so teams don't have to carry their supplies to and from the propulsion lab whenever they need to make modifications. They can set up their tests on site. So that's a brief introduction to the project, and I'd like to introduce Cameron Kurtz to discuss the design solution for Janus.
Thanks, Rachel. So, as mentioned previously, this is going to be flown in the FAR Mars competition. And with that comes a set of requirements. One requirement by the FAR Mars competition is that the vehicle must be passive in stabilization and must have a total impulse limit of 9,208 pounds per second. Due to engine imperfections, a 12-second false tape burn will be the requirement to deliver the quadrilateral fold. In traditional manufacturing, so no 3D printed additive manufacturing, and no expensive hard machining exotic super alloys. The final requirement is the chamber must be pliable. So one of the use requirements, the engine is going to be designed for 1,000 tons of thrust. This will provide enough thrust to ensure the vehicle is pulling 5 to 6 G's at launch, which is a good rule of thumb to ensure that the passive is stabilized. Plus, it gives enough margin in case there is performance issues with the engine. our vehicle stream. The injector type is a lock center pistol injector. We'll talk a lot more about this in a little bit. The cooling type is ablative with fuel film cooling. An ablative is basically material that chars away when heated and creates a thin layer of true gas. This is important because it will help insulate the combustion chamber from the hot combustion gases. On top of this, we're going to film cool, FFC, meaning that we take some percentage of the fuel and inject it onto the chamber wall. And this is also going to create another insulating barrier between the hot combustion gases and the blade chamber. Just to emphasize what a lock-centered pistol injector is, this image is from Purdue. Typically, this is their injector for their Mars competition rocket, and it is also a pistol injector. On the left-hand side is the angular flow, and on the right-hand side is the radial flow. In our case, the angular flow would be jet A, which is our fuel, and on the right-hand side, our radial flow would be liquid oxygen. So you can imagine both of these going simultaneously, including 90 degrees to each other, creating a common flame downstream of the fuel. That's what a chemical injector is. Here's an image of the injector cross-section. Everyone should have this image in front of them. The image you have in front of you is actually a one-to-one scale of the injector. So what you see on this paper is how big the injector will be in real life. On the left-hand side is engine components. So these are things that the team has to manufacture or fabricate. And on the right-hand side are features. So these are things that are designed into the injector itself. So to start off, here's an image of the pintle post. The pintle post is arguably the most complicated on the injector. The purpose of the pintle post is to center the pintle tip inside the engine and provide fluid connections to the feed system. Now, immediately see the image is green and red holes. Green holes indicate clearance, and red holes indicate red holes. So these fluid connections can be created for the feed system by welding 7 swage lock fittings to the post itself. In the image of the injector cross-section, you can see a cross-section of 3 of the 7 fittings, 2 symmetric fuel ports, and 1 axial oxygen port. Behind them are 4 more fittings. 3 of those fittings are for measuring pressure directly off the injector, and another one is for fuel cooling. So the pintle post threads connections, but it also centers the pintle tip, and it does this through a cylindrical lip. And the cylindrical lip is a very tightly toleranced feature on the pintle post, and it mounts to the faceplate. The purpose is to maintain the annular gap. The annular gap is extremely small. It's 15,000 millimeters, 0.015 inches. Very small. So it's important to be able to maintain this concentricity when assembling the engine. So this cylindrical lip will provide that. On top of this, it will often be difficult to remove the pintle post from the faceplate, so jack screws will be added to the pintle post as well. So it will make assembling this assembly significantly easier. So the pintle post mounts to the faceplate, and the purpose of the faceplate is to manifold propellant for the combustion chamber. So the faceplate has 2 separate plenums, an outer plenum and an inner plenum. The outer one is for fuel film cooling, and the inner one is for main components, main fuel. So for those that don't know, a plenum is basically a pocket or cavity that is inside of the injector that manifold propellants. So in our case, we have 2 of them. We have a separate fuel film cooling plenum because we don't know how much the engine needs to film cool. There are a lot of guesses we're making with the injector for the engine. We don't know how much we need to film cool and what the technical weight is. And so by having this separate plenum, it gives the team the option to change how much the engine film cool. It does this by, if you can change the pressure inside the plenum, you can then change the mass flow. So having the option to change the mass flow, how much engine film cools, will allow machine this one, but unfortunately it's going to be remachined due to a slight design change. But you can essentially imagine a ring with a bunch of holes around it. The purpose of this distribution ring is to ensure the fuel is being symmetrically distributed into the angle. It does this by having a pressure drop of around 5 psi. So this low pressure drop ensures that all the fuel will be symmetrically uniformly pushed around into the angle of gap. One great thing about this distribution ring is it is modular, so we can remove it, replace it with another one if it's not working. So it allows the team to tune the engine and solve any problems with symmetry. The Tyndall tip is what injects the oxygen into the combustion system. And when you get a copper, because copper is much more likely to be able to take the heat of combustion. And it's swing from the machine and enable-based fuel, which can also take the heat. One great feature about this Tyndall design is the logical drive. The hexagonal drive is a high-force drive used on decking screws. Since we're going to be torquing and untorquing a lot, taking it apart, inspecting it, this high-force drive is easy to install and install. What it also does is if we damage the Tyndall tip, we can easily remove it without having to replace it with components. It also, on top of this, allows us to easily change the jet element inside the slot, inside the hole. So it allows the team to easily chase combustion efficiency. I'm sure SpaceX has been thousands of tips trying to optimize their own combustion efficiency. And this is just an attempt to do that as well. So the film jacket is fastened to the base plate with stainless steel subframe chapters. And the purpose of the film jacket is to protect the film jet or the engine combustion chamber and create curved surfaces with easy recirculation. All Tyndalls have recirculation zones, and these recirculation zones is what enables good mixing. And so in order to encourage this mixing, all Tyndall injectors have curved surfaces where you roll it in. And so the slim film jacket creates these curved surfaces to encourage recirculation to the internal good performance. And secondly, it protects the slim film jets because the slim film jets are injected behind the film film jacket. And if they're injected behind it, it gives the jets a chance to do their job, which is protect the ablative combustion, support it enters the hot combustion gas recirculating them. So the firm component is the chamber plan, and the purpose of the chamber plan is to secure the injector to the ablative chamber. And it does this by using RTD to bond the chamber plane to the ablative. And once it is bonded to the ablative, you then take carbon fiber and you wrap carbon fiber around the outside of the chamber plane and onto the ablative chamber. One critical thing on the chamber plane is the bump. The bump is absolutely critical. This is what actually retains the ablative chamber to the chamber plane. Without the bump, when the engine static fires, it would shoot 100 plus feet down. So the bump is absolutely critical. Another thing the chamber plane does is it provides a pressure port for measuring chamber pressure inside the engine. So a welded space lock fitting will be added to the chamber plane so we can measure engine pressure. And the final thing to note is the chamber plane is going to be machined out of aluminum. One, aluminum is lighter, which is good for the vehicle. But two, the chamber plane is disposable. Once you bond the ablative to the chamber plane, you can wrap it with carbon fiber. It is permanent. You cannot undo it. So every time you hot fire the ablative, you have to make a new chamber plane with it. And so by using aluminum, it is one, cheaper to make more chamber planes, but it's also easier to machine. So chamber plane will also be made out of aluminum for those reasons. I'd like to pass it off now to Ahmed to talk about Heatsink and the ignition tank.
So starting with the ablative. The ablative chamber is basically made out of, it's going to be made using the mandrel. The mandrel is a negative mold of the chamber, where we're going to be wrapping silica tape around it. After that, when it's taken the shape, it's going to be reinforced again with the high temperature epoxy. Unfortunately, the silica tape with the epoxy by itself wouldn't be able to withstand the internal pressure of the combustion chamber, so it will be rewrapped with carbon fiber, film binder. Moving to the heatsink. The heatsink will be our second method of cooling in the chamber. This heatsink would allow us to do multiple short-time testing, and it would also allow us to test only the injector blade without having to worry about other things. When you design or make a heatsink chamber, you look for a material that has a really high thermal conductivity or a high melting point. Copper is a very common material used in combustion chambers. Since it wouldn't fit in our budget, we end up using bronze since it has a really good thermal conductivity in comparison to steel. And then for the throat, we end up using graphite insert since the graphite has a really high melting point. The chamber is going to be 13 inches long by 7 inches in diameter. And finally, the ignition system for the engine. The ignition system, we want it to be repeatable, more burn time, and flame spread. The reason that we want more burn time is because you want to start your ignition system before you start injecting the propellant into the chamber to avoid hard start. So what we end up doing for that, we're going to put a small solid rocket inside of the chamber, and that will be pointing toward the pintle tip to ensure there's a successful instant ignition. I'll pass it up now to Luke. We'll talk about test cell 3.
So moving on to the test cell that we're going to be testing Janus in, as well as future engines. We are making our test cell out of a prefabricated Connex box enclosure. These Connex boxes are very versatile and they're very common and easy to obtain. Plus, they are a very strong structure for us to modify into the test cell that we need it to be. Next to our test cell will be an external concrete pad, which we'll put our liquid oxygen and nitrogen tanks on, which will be used to pressurize and feed our system. Our test cell will be placed adjacent to the existing test cell 2. As you can see in the photo in the lower right, there will be a catch fence downrange of the test cell, which will prevent any debris from reaching a public trail, which is behind the testing area, which will be closed, but we have had issues in the past with people and animals entering that area even when it's closed. So we just want to make sure everyone's being as safe as possible. And then you can see an orange dot in the picture, which represents a data and power post, which runs data and power from Building 91, which is going to be our control room for our testing. And that allows us to connect our instrumentation and sensors and valves and everything during testing, and then we can safely store our wiring harness inside our test cell when we're not testing. Obviously, safety is a huge concern for this project since we are dealing with some flammable materials in an enclosed environment, so we're taking lots of precautions to make sure that we can test in a safe environment. We are adding lots of vents and doors to allow for proper ventilation throughout this test cell. Besides the 2 large doors you can see at the end of the test cell, we are adding some double doors by where our fuel tanks will be stored, as well as another door on the opposite corner, and then multiple vents in the roof and walls of the test cell, which will allow ventilation even when we're not testing. Additionally, we have 2 layers of blast protection for our tanks. We have one on the red thrust structure, which I'll talk about in a minute, and another sheet of steel on the tank structure itself, which will protect our tanks in the event of an explosion. Since it's very dangerous to be in a test cell when tanks are pressurized to high pressures, we will not be in the test cell. We will all be in Building 91 anytime our tanks are above 60 psi. And this is to make sure that we're safe, and we will be monitoring our tanks and our testing using remote cameras while the tanks are pressurized. In addition to what I've talked about already, we're establishing strict safety procedures with campus safety and the College of Engineering to make sure that not only us, but future teams who maybe don't have as much experience testing rockets can test in a safe environment. One more thing in the photo here, underneath the thrust structure in the fuel tanks, we are replacing the wood flooring of the test cell with diamond plate steel, which is a safer environment in the event of a liquid oxygen spill. Moving more to the interior of the test cell, there are 3 main systems that support our tests. These are the thrust takeout system, which I'll talk about here in a minute, our feed system, and our instrumentation data and acquisition. and control system. Behind those systems is a storage and work area with several storage shelves and workbenches, which, as Rachel talked about, allows us to build some of our components on site rather than having to run back to the propulsion lab anytime we want to build something. Additionally, underneath the thrust structure there is a reinforced floor structure which allows us to transmit some of the thrust of the engine safely to the frame of our test cell. Going more in depth on that thrust takeout system, this system is designed primarily to hold our engine horizontally above the floor of the test cell, pointed out the doors at the open end of the test cell. And the steel structure is designed to support 5,000-pound thrust engines with a factor of safety of 2. This is to account for hard starts, as Cameron talked about earlier, where cooled propellant ignites, and also to account for possible errors in manufacturing, so we want to make sure that we have a strong structure that can support our engines. Attached to this thrust takeout system are 4 load cells, which you can see placed around the hole in the center of that large plate there. Those load cells measure the thrust of our engine and help secure it. Next to those load cells is an interchangeable engine mount. This is the only part of our thrust takeout system that is specific to each engine. So this engine mount is designed for Janus, and that just means it has holes in the specific places where fuel and oxygen will be entering the engine, as well as holes for the mounting bolts for that engine. So future teams, the only thing they'll have to redesign is that engine mount just by moving around the holes to where they need and water jetting a new piece. The mounting plate, which is the large red plate you can see there, is one of our 2 layers of blast protection, and that's what the load cells mount to. There are multiple holes, so you can move the load cells around if you have a different sized engine being tested. And that mounting plate transmits the force to the welded steel beams, you can see, which transmit it down to the floor. Those 4 L brackets along the floor are welded to the reinforced floor structure that's underneath the diamond plate steel, and that safely transmits our force. We have already manufactured this red thrust structure. You can see it in the picture in the upper right-hand corner of the screen. I will now turn it over to Daniel to talk about our feed system.
So, So the feed system is what actually provides the propellant to the rocket engine. It's made up of all the components that are required to do this, such as the cryogenic ball valves, pneumatic actuators, tubing, and fittings. The primary requirements that drive the design of the feed system are that it needs to support engines capable of 3,000 pounds of thrust, and that it needs to be a safe and long-lasting facility. So the specifications we've developed to meet these requirements is that they'll be capable of operating at 750 psi. This is so that it can provide the required 9.5 pound mass per second of liquid oxygen, which is needed for a 3,000 pound thrust rocket engine of moderate performance. We will be pressurizing with mechanically regulated nitrogen and be establishing mass flow rates with cavitating Venturis. Flow control will be done via pneumatically actuated ball valves. So this is a very high-level flow and pressure diagram. The panelists should have an 11 by 17 copy of the full plumbing and instrumentation diagram. So in the top left-hand corner, we have our high-pressure nitrogen cylinders. These provide the nitrogen to the high-pressure nitrogen distribution circuit, which then supplies the nitrogen to our propellant tanks and the muscle pressure circuit. If we take a look at the liquid oxygen pressurization system, we see that the nitrogen is regulated down via a mechanical regulator. This then goes through a check valve, which is to make sure that our oxygen vapors and fuel vapors aren't mixing, and then through a filter, which is to catch any debris created by check valves, since they like to chatter. We then go through LOX press, which is the liquid oxygen pressurization valve. This allows us to remotely pressurize the facility while we are in the safety of Building 91. And then down into the liquid oxygen tanks and into the run line. FMO1 is our cavitating Venturi, which establishes a constant mass flow rate, which then goes through our main oxygen valve and into the rocket engine injector. In the middle is the muscle pressure circuit. This circuit provides the required pressure that the pneumatic valves need, as well as supplying nitrogen to our purge valves, which allow us to displace any remaining fuel or oxygen downstream of our main valves, allowing us to shut down the engine cleanly. If we take a look at the pressures, our high pressure starts at roughly 3,300 psi. We then regulate it down to roughly 550 psi. This pressure was calculated by taking into account the required injector pressure, and then accounting for losses in fittings, tubings, and the Venturi. A very important thing to note is the pressure drop across this Venturi. It goes from 550 psi to 378 psi. This large pressure drop is to make sure that we are always in cavitation, ensuring a constant mass flow rate. If your downstream pressure goes to roughly 80% of your upstream pressure, you can get knocked out of cavitation and you're no longer supplying the correct mass flow rate for your rocket engine. One important thing to notice on the fuel side of the circuit is that we have an orifice right here, which is swappable. So we can provide film cooling at different pressures, and we can tune that as we test and see what the engine requires. So the cavitating Venturis are one of the most important components of the feed system, and they're being designed, manufactured, and tested in-house. These cavitating Venturis ensure a constant mass flow rate by creating a choked condition at the throat of the Venturi. The flow is choked because cavitation is occurring, and this cavitation creates dual phase flow. The dual phase flow then drops the speed of sound to roughly 30 feet per second. The reason we're getting cavitation is we increase the fluid's velocity to the point where the static pressure drops below the vapor pressure. We've designed a flight Venturi, and we've also designed, built, and tested a demonstration Venturi. This demonstration Venturi is designed to work with water, be pressurized off shop air, and utilize existing hardware. We have tested this Venturi, and the reason we designed this demonstration Venturi is to validate our design process and make sure we know what's going on. This is the results of one of the tests. In orange, we have the downstream pressure, and in blue, we have the upstream pressure. As we increase the downstream pressure, we see that the upstream pressure remains very steady and constant. But as we get above roughly 80% of the upstream pressure, we are knocked out of cavitation, and we're no longer decoupling the upstream pressure and the downstream pressure via choke condition. When we go below our recovery pressure, cavitation resumes, and we are now decoupled. I'd now like to hand it off to Rob to talk about the lock sinks.
So another key part of the feed system is the liquid oxygen tanks. These are some of the requirements. The first one was that it must support a 15-second hot fire for Janus. This was created by taking the required mass flow rates for the engine, incorporating chill and incorporating oil off. This yielded a volume requirement of roughly 20 gallons. The liquid oxygen tanks must also be mounted above Janus. This is because if they were mounted below, the feed lines would have to be routed upwards, which could introduce bubbles into the flow. They also must be structurally sound to 1.5 times our hydrostatic test pressure. This pressure is the pressure at which we fill the tanks with water and pressurize this water to test that there were no critical design errors or manufacturing errors. So we wanted the theoretical burst pressure to be at least 1.5 times this. It also must include a dipstick and diffuser. You can see a picture of this right here. The diffuser is in the front with all the holes in it. The purpose of this is it takes the nitrogen pressurant and directs it radially so it does not directly make contact with the liquid oxygen and boil off a large percentage of it right away. And the purpose of the dipstick is that it is a small pipe that is about 2 inches into the tank, so that when the liquid oxygen tank is full, this would push some of the liquid oxygen out of the tank, and it would be a visual cue to know when the tank is full. This acts as a redundant method in case our sensor in the tank were to fail. Next, we have the important pressures related to the tank. The first one is our leak-checked pressure. This is important because it is the highest pressure that the tank will be at while people are around it. It is at 60 psi. You can see the factor of safety is very large at over 30 feet. Next is our run pressure. This is the pressure we expect to be at during a hot fire at 550 psi. Next is our relief valve pressure. This is if the pressure were to ever get above 750, these relief valves would actuate, reducing the pressure back below 750. We also have burst discs set to rupture at 850 psi. This is in case there were multiple failure modes. These could fully evacuate all the pressure in the tanks very quickly. Our hydrostatic pressure was set to 900, so just above our burst pressure. We just conducted these hydrostatic tests yesterday, and both tanks passed. So there were no critical manufacturing or design errors up to 900 psi. Also, our theoretical burst pressure is 2,300 psi, so well above that 1.5 times hydrostatic pressure requirement. These are some of the major design choices for our liquid oxygen tank. We chose to use stainless steel 304 as our material. This is because it offered a good balance between cost, LOX compatibility, and strength. The two other alternatives we could have used were aluminum or stainless steel 316. Aluminum is weaker, and it also has problems with cryocycling. 316 is stronger and more LOX compatible, however, it's much more expensive. We chose to use flat end caps to seal these pipes, primarily because we could manufacture these in-house. The alternatives would have been elliptical or spherical end caps, however, we would have had to order these, and the estimate for this was over 2.5 months. We chose an 8-inch diameter pipe for a couple of reasons. The first is that this is the largest diameter where flat end caps are still feasible, so if we went bigger than this, we would have had to wait those 2.5 months. In addition to this, the pipes that size were very expensive. If we went down to 6 inches, we would have had to increase the number of tanks to 4 rather than 2. This would increase complexity, not only in manufacturing, but also in operation of the test cell. This is the tank mounting structure along with our DAC box. You can see in the back, these are the 2 liquid oxygen tanks along with insulation around them. We plan on using expanding foam for this insulation. In the front, you can see our fuel tank. This is 6 inches in diameter and made out of aluminum. This is existing infrastructure. This was actually the liquid oxygen tank from a previous project. It's been hydro tested and used already, and we are going to hydro test it again. Aluminum is not an issue in this case because our fuel is not cryogenic. The mounting structure itself is made primarily from tube stock. This because it's readily available and we can manufacture this ourselves. And on the right, you can see the data acquisition box. This encompasses a lot of our data acquisition equipment in case an engine blew up. All this expensive equipment would not be damaged. You can also see Unistruct right below the tanks, and on the top, this provides adaptable mounting and also a place to mount all the feed system components for this. I'll now pass it off to Shubra to talk about data acquisition.
So in order to equip our test cell with liquid rocket engine testing capabilities, we need to be able to measure parameters such as pressures, temperatures, tank levels, and forces. So this is our instrumentation schematic, which is a conceptual layout of the location of our sensors within our feed system and our engine. These sensors will provide us with measurements that will help us verify the performance of our engine, the overall functionality of our system, and also the safety of our system. Like Rachel mentioned earlier, all our instrumentation is modular so that teams that want to use Test Cell 3 in the future can swap it out for whatever better suits them. Thus, we have picked sensors that best suit our needs for Janus. The sensors that we've picked are the lowest cost versions available that meet our needs for range and accuracy. We have picked S-type load cells to measure our thrust because they mount axially between our thrust structure and our engine, the locations of which Lucas mentioned earlier in his thrust takeout slide. We have picked pressure transducers to measure our pressures because they are accurate, relatively easy to install, and also respond well over a wide range of pressures. We'll be using 1,500 psi pressure transducers for our LOX and fuel line, and 150 psi, 1,000 psi pressure transducers for our LOX and fuel line, and 150 psi pressure transducers for our gaseous nitrogen line. We'll be using type E thermocouples for our cryogenic temperatures because they are made for the low temperatures that we are expecting, and type K thermocouples for all our non-cryogenic temperatures because they are more suited for our high operating temperatures that we are expecting. Lastly, we'll be using capacitive level sensors to measure our tank levels. This is the more interesting of all the sensors that we're using because we're manufacturing it in-house. This is because to modify the commercial versions of capacitive level sensors is very expensive. So we will be making it specifically for our tanks on campus. So a little bit about our capacitive level sensor. It has an outer tube and an inner rod separated by a dielectric fitting. So when the liquid level rises between the outer tube and the inner rod, the dielectric constant changes and thus the capacitance changes. To measure capacitance, we will be measuring the voltage change across our circuit, which is in red in the lower right. This voltage change is in response to a pulse input that we will provide, which is in blue in the lower right. This will help us calculate our time constant, which is related to capacitance, again, as can be seen in the equation in the lower right. Once we have our capacitance, it will correspond to a certain tank level, and this is how we will determine our tank levels within our system. Once we have all the measurements from all our sensors, we will feed these measurements into our software. The software in test cell 3 will be in two parts. All data acquisition will be done through LabVIEW, and all controls will be done through Arduino IDE. The LabVIEW code will take all measurements and process each measurement, however that particular measurement needs to be processed, and then perform the necessary functions such as indicate the values on our user interface, record all data, and other relevant functions that you can see up there. The controls code will control all valves within our system and also display all valve states on the Arduino control panel. The controls code will also interface with the LabVIEW user interface to display all valve states there as well. When the time comes to test our engine channels, the controls code will run the automated engine testing sequence as well. Another key component of the software in test cell 3 are our emergency responses. We have 3 lines of defense against any unforeseeable circumstances that happen that justify shutting down our test. The first of which is the LabVIEW red line auto abort. In this, the LabVIEW code will be constantly comparing all measurements to red lines set by the feed system and the engine teams. If any measurement exceeds beyond the critical max or lowers beyond the critical min, LabVIEW will automatically instruct Arduino to shut down all testing and put the system in a safe configuration. Our second line of defense is an actual abort button on our Arduino control panel. A user can press that button, which will instruct Arduino to then put all valves in their predetermined safe configuration and shut down testing. Our last line of defense is our emergency stop button, which is independent of all software and is hardwired to all all valves. If a user presses this, again, it will instruct all valves to be in their safe configuration and shut down the testing. So we have these procedures that will work with the infrastructure safety considerations to make sure that test cell 3 is a safe environment for people to work in. I will now pass it off to Rachel to talk about the controls part of our software.
The control logic for test cell 3 can be thought of in 3 main stages of operation: manual control, running the test, and ending the test. During the first stage of manual control, the user has control over the valve states. There are toggle switches on the control panel that the user can use to instruct the test cell to actuate the valves during the filling and chilling process. There is no set procedure for either of these processes, so the user needs to be able to change the valves manually during this stage. It's important to note that during this stage, propellant flow will be disabled, so the main fuel and main oxygen valves will not be able to be actuated and keep the test cell in a safe configuration. So if the user tries to actuate a valve that would result in an unsafe state, then the system would block actuation and continue manual control. Once propellant flow is enabled and the user has pressed the automatic test sequence, the test cell will cycle through the test sequence defined by the user, continuously checking for 3 conditions. First, it will check for the red line auto abort coming from LabVIEW, indicating that one of the measurements has exceeded a critical value. It will also check for whether the user has pressed the abort button on the control panel, and it will check for whether the user has disabled propellant flow. So there are 2 options on the control panel for the user to manually disable and auto abort testing. Regardless of whether the test proceeds nominally or is aborted, the test cell will return the valves to a safe configuration and then restore manual control to the user so they can either run another test or shut down operations for the day. Diving a little bit into the control panel and the test sequence, the control panel, you can see at the top, there are three main buttons, the flow enable, automatic sequence, and abort buttons. These give the user control over the test sequence. At the bottom, you can see all of the toggle switches to manually actuate each of the valves as well as the igniter. Finally, you notice the colored circles next to each of the switches. Those represent light-emitting diodes that correspond to each system that switch is a part of. So each valve is connected to a limit switch. So when the valve is open, that switch closes and visually verifies the state of the valve, and the user can check whether the valve actuated or not. The baseline architecture for the test sequence is a user input state diagram to the Arduino. Here is a sample state diagram where a 0 indicates a closed valve and a 1 indicates an open valve. So here, at time equals 1,000 milliseconds, valve 2 and valve 3 both open. The control panel cycles through the sequence and continuously checks for those abort states. And finally, restores the test cell to a safe configuration for the user. That concludes the technical portion of this presentation, but I'd like to discuss a few administrative items before opening up the floor for questions. The project has garnered funding from sources both internal and external at Embry-Riddle. We have funding from the College of Engineering, Student Campus Enhancement Fund, as well as sponsorships from Far Mars, Vector Space, and Stellar Explorations. These total $62,800 to be used in the development of both Janus as well as the test cell. Additionally, we've received donations in the form of equipment from the Embry-Riddle Propulsion Lab, ValWorks, and Astra, which will help us save money on parts and use the donations within the test cell. By contrast, our expected cost for the project is $57,000, including all of the work for Janus, all of the hardscaping and conduit that need to go into test cell 3, as well as the enclosure and all of the test cell 3 subsystem. All of test cell 3 subsystems. This results in almost a $6,000 margin within our budget, so we will be running on budget and on schedule. This team has put in a lot of hours on this project, over 2,100 hours total since September. When comparing this to the expectation that we would work just under 1,900 hours, you can see that we put a lot of work into this. The expectation was that each team member would put in 2 hours of work outside of class for every hour spent inside of class. And we also decided as a team that each team member should dedicate 12 hours per week specifically to engineering design work. In the future, for next semester, we're looking at installing our Connex box and finishing all of the hardscaping by January 21st of 2019. In February, we will finish manufacturing and installing all of our subsystems. You've already seen that we've manufactured our liquid oxygen tanks and our thrust structure, and we still have some components of the feed system and instrumentation data acquisition and control to install and manufacture. In March, we will run cold flow tests of the engine and verify that the system is working the way that we need it to. And then finally, by May 4th of 2019, we intend to have the first successful hot fire of a liquid rocket engine on the ERAU-Prescott campus. This project could not have been possible without the help of so many different campus entities. Most notably, Dr. Elliot Briner, thank you so much for your mentorship and support throughout this project, coming out of the woodwork to support the development of Test Cell 3. It could not be possible without Dr. Briner. I'd also like to thank other Embry-Riddle faculty, Dr. Haven, Dr. Fabian, Dr. Garrick, Dr. Mather, and then also Dr. Ayers, who was kind enough to join us today for his support of the project as well. I'd like to thank the Cameron's mentors at Astra for their support and technical guidance in the development of Janus, and then finally all of our monetary and equipment sponsors. Your donations to this project make Test Cell 3 possible, and we're excited to see it become a reality next semester. And with that, I'd like to open up the floor for questions.
You guys need a mic?
If you can hear us, then that'll be okay. You want to sit on?
He's muted himself, so he can unmute
Okay.
any questions.
Wow. There's a lot of stuff there, guys. They could tell you put a lot of work into this project.
a lot of passion from a lot of members of the team, and it really shows with the quality of the presentation as well as just the technical content that's included. A lot of good stuff, a lot of really, really great stuff. So I just want to ask a couple questions that have probably been thought of as part of this design process. Start with slide 4, which is an overview of the test cell 3 plan form. It doesn't appear that there's any sort of physical barrier between the test section where the motor and other auxiliary equipment is and the rest of the storage and workspace. Is that intentional, or is there a reason that you wouldn't want to, kind of isolate the two major elements of this to protect one from the other?
Yeah, who can speak to that?
Yeah, so our primary safety concern for if an explosion were to happen is protecting our tanks. We anticipate that if an explosion were to happen, it would primarily damage the tank area, and that's what we want to protect. If anything else farther down the test cell gets damaged, that's a very minor concern in comparison to the tanks getting damaged, so that's where we put our focus.
Okay, so, okay.
And one thing, and another important thing too, that is we are, one of our most important safety considerations was safe egress. So if anything were to go wrong while people are in the test cell, we want them to be able to escape in either direction. So if we had a ball in that center, then that makes the egress to the one-man door a little bit more difficult. So, and it also provides better ventilation too.
Excellent. Those are great answers. Thank you.
The wall also costs money.
A fair answer as well. Okay, so the next is starting to talk a little bit more about engine design, primarily the manufacturing of your ablative jacket. It looks like in one of the pictures that you had started, it's in slide 15, it looks like you've made a prototype, or what is this image? Can you talk a little bit about what you maybe learned through building of this? I'm not familiar with building ablative.
So, and the picture that you see in the bottom is basically we had a 3D printed model of the mandrel, and we started wrapping and practicing fiberglass around it. I think the thing we couldn't separate it from each other very well because I think we didn't put enough mold release, and it was the first attempt to ever make an ablative chamber.
So you just made the one then so far?
Yes, yes.
All right, great. So I think practicing that process will help a lot. Are you doing any sort of compaction after the winding process to minimize voids or anything like that?
As far as I know,
Okay.
So the ablative isn't actually getting filled in. We're manually winding the ablative, and then the.
By winding it.
Sorry, yeah, you're right.
Okay.
There's no filament winder like it.
Fair enough, right, it's not a machine process, I
Yep.
understand.
Yep.
So I think adding some sort of a compaction element to when you're curing it, the epoxy element would eliminate any chance of having some voids or some other dislocations or something like that. Just a suggestion. I'm really surprised at the choice to use the almost single-use type chambered flange. Manufacturing that aluminum piece is going to have a lot of, there's still time and energy that goes into that. And I would look for any possibility to more modularize that system and see maybe what some other groups are doing if there's any opportunity for that. Just to kind of keep the reuse cost down when you do a test and it aborts after 1 second. Well, I guess that means we have to continually make more and more of these single-use elements of it if we need to. You are making, I missed the detail, I guess, that there are two chambers, a heat sink chamber for short duration testing and a flight chamber, or
yes.
is that correct?
Yeah, so the heatsink also would allow us to only test the injector plate without having to worry also about testing the ablative, and would also allow us for short testing. So short duration, maximum 4 seconds will be.
And then my last question is overall on the engine design, you've got to be looking at, what your overpressurization conditions are going to be. What fails first? What does an unpredicted, unplanned overpressurization event look like? Looking at this cross section here, where is your weakest point? Where are you planning or expecting it to let go?
Cameron, did you hear that?
Yeah, I think so. Can you hear me?
Yep.
Yeah, okay. So I so there are a lot of failure points on the engine. Like it's hard to figure out what's going to fail first. Most likely place to fail is the pintle joint. That's where you thread the pintle tip into the pintle post. Very likely will potentially burn out a pintle tip trying to dial that in. The actual joint itself, I spent a lot of time trying to calculate like the stiffness coefficient of the joint, trying to exactly calculate how many fasteners you need. I got around 18 fasteners in total, quarter 28 alloy steel cellular cap screws. Burst pressure, I believe, is around 2,500 psi. So I'd imagine somewhere around the chamber flange that would like rip the threads off the nuts or off the bolts, and it would separate there if the pintle joint didn't break first. So that'd be my guess.
Cool. But it's always just good to kind of plan for those types of events. I mean, during a hard start or something like that, where you risk over pressurizing that chamber. What are you sending downrange, and what pieces are you expecting to see from that? Kind of helps to mold what your safety plan is going to be from that. So, really nice job. Very impressive. Nice job.
Yeah, I just want to say this is a lot of good work, and I'm admittedly unfamiliar with rocket engines, but taking what I know and looking at it, I don't know what the normal component design or structural design process is. It seemed like there were times where you mentioned this is designed for 5,000 pounds, and this is designed for this many. It would have been nice to see some analysis artifacts. I don't know if you have any backup slides or what degree of structural analysis you guys normally do for these types of projects. See, look.
Yeah. So I can talk a little bit about that. So we've tested our entire thrust takeout system to 5,000 pounds. We know that the feed system supports about 3,000 pounds of thrust, but we want to give a little bit of extra margin to account for maybe off-axis thrust. We know there's been talks about possibly testing a gimbal for an engine, so we want to make sure that we have enough strength there. So yeah, we've been doing finite element analysis, mainly using Autodesk Inventor. But as we move more into the manufacturing stages, we'll be backing that up, and we've done a little bit of hand calculations to validate some of our more critical calculations as well.
So you apply the same velocity to the motor itself. I don't know what degree you usually apply that to all the motor components, but you want to walk me through that, or?
Cameron, do you want to talk about ANSYS on the engine?
If you want me to. So I did ANSYS analysis on every single component on the engine. Or at least I tried to. I spent, I'd say, around at least 100 hours trying to do it with every single component. It's pretty hard to do on something like this. Like the main thing is trying to find the heat transfer coefficients on inside the engine. It's basically it's very hand wavy. A lot of it's black magic, and just because RPA gives you a number or you think it's a number, that doesn't mean it's going to be true. If you don't set up ANSYS correctly, it will give you invalid results. So there's a lot of things going on here. Doing the ANSYS analysis, I was able to find stress concentrations, and I was able to get a predicted temperature of around 1,000 degrees at most at the 12-second qualification burn towards the end of the engine. But that's all the analysis that was done.
Yeah, I just wanted to see what you guys have done with that, because I mean, if you're going to be running it, I'm sure you'll have more detailed information next semester, but I'm kind of from outside the rocket engine test community. I know it's kind of a technical community on campus, but just from my outsider point of view, I'd like to know more about that before you run something possibly pull up. But I'm sure you've come through that. Slide 37. I just wanted to commend you guys on having that well thought through force logic in 3738. So that's really good to see that you thought through that. And then the last thing, just a very small comment. So you said on schedule, on budget. Show the schedule.
Okay.
Kind of where you guys are at. Where you expect to be based on these things. So
Okay.
great work, guys.
Thank you, appreciate it.
Absolutely outstanding. I expect nothing less from you. You guys have an incredibly My biggest concern is your schedule, not showing that. Bigger than this, but, and then also I see that you are looking to do your first hot fire on May 4th, which means you have absolutely no schedule margin, which is, for this ambitious of a project. Frankly, I would be looking at, if you don't already have an extremely detailed schedule, down to that no task on that schedule is more than a week long, better yet a day. That and monitoring that on a daily basis of where you're at. You don't have that, do that.
Okay.
And as you do that, find a way to build some margin in. You gotta just assume those May 4th is not the date, April 4th is the date.
So, yeah, May 4th is the last possible day that we hope to have by. Early as possible is probably spring break.
Yeah. So what I meant to say there was that we would have it tested by May 4th, not on May 4th. So that's graduation. That's the day that we can't test anymore.
Well, we did test MP1 3 weeks after graduation, so.
But yes, you're right. We should have a detailed schedule, and we'll be working on a very detailed manufacturing, implementation, and test plan for next semester.
It's critical to manage the project at this stage.
Yeah.
And then just one small kind of following up on something Bryce said on your, you call those things, the chamber flanges, the fact that if they're not reusable, then make sure you buy some in volume if you really intend to be doing this. And I know it's not part of your capstone budget to do more than one, but let's figure out a way, because we got a lot cheaper to buy them in volume.
Thank you.
Well, you guys have been answering my questions all semester, so I'm going to pass.
You mentioned during the e-stop process, the valves going to go back to a safe state. You're worried about whether they go back to the safe state if there's a power outage.
Yes.
Yeah, so, with the power outage, they default to their normally open or normally closed state. So for our vent valves, that's open. For our main valves, that's closed.
So there's some sort of spring or something.
Yeah,
Yep.
Even the, we have both spring return and pneumatic, or air return valves. Both of them return to whatever condition if electricity fails. If the air pressure fails, our spring return ones will automatically go back, and so we have those on the very important areas like vents or our crude valves. And then the pneumatic ones, if this air pressure fails, they'll remain in their position.
What kind of protection is around your IADC box?
Yeah, it's a Pelican case, so that is, that's a very sturdy case. We understand that in the event of a tank explosion, it's very unlikely. We've taken a lot of safety precautions to prevent that, but we understand, and the university understands, that in the event of a tank explosion, that the system's just going to be gone. Yeah, so we have the Pelican case in place to protect them from other things that might get in the way, maybe an engine explosion if a piece of something gets that far back for some reason. But in the event of a tank explosion, we do understand that we would lose the entire system.
And will there be cautious signage out there on your cells? I think we've got these kind of things inside.
Yes. So during testing, we'll be working with our safety and security department to close off the area. Luke mentioned that we would be closing off that public trail back behind and let the entire campus know that there's a test going on at that time and to stay away from the area unless you're on the team.
Minor point on your PID diagram.
Yeah.
Out on the railroads, every time you do a revision, they're going to do, you did part of the revision letter in this case, and the date, but it also should be a one-line sentence of why did you actually do the revision.
Okay, so I've been keeping a rev log that tracks all the changes, and then I've been doing the lettered revisions for just like internal releases, and then when we release to manufacturing, we're going to rev it to a number. That's a good idea. So we've, well, first we built and tested the capacitor level sensor, this guy right here, and we've seen it work with water and the capacitance that rises, and it's been done before too by other rocketry groups.
So you're kind of copying design, not having to start from scratch.
Well, so there's one design that exists where the component where we realized, oh, you can do this sort of thing. The cool thing about this, and I haven't seen it done anywhere else, is it's done completely with commercial off-the-shelf fittings. Swagelok makes a dielectric fitting that can separate the rod from the tube, and so this cost $150 and took us 30 minutes to build, and then we were able to test it in 5 minutes. So that's really cool. But on the liquid oxygen side, we have
Sure, so we have the dipstick, so if the tank level was to rise below about 96%, the pressure will push the liquid oxygen out of the tube, and you can visually see that it's cold. However, there wouldn't be a way to realize when it was empty in the engine.
Yeah. So having the capacitive level sensor is not a critical feature, but it is nice to see our tank levels decreasing with our tests. It's another way to verify our mass flow rates, but hasn't been used in the past and is not an absolutely critical feature of the system.
That's it for me.
Thank you.
Nice job. That covers the question I had.
I just have one short question. In order to make this into a flight vehicle or a flight engine, how much modification is necessary?
I'll just answer that since the flight engine, the ablative, it's 1-to-1. And we've been working with Nate DePutter, who's no longer here, but he's leading up that flight vehicle. The interface point is the plumbing and the actual physical bolt pattern, and we've been working with them on the bolt pattern as well as the fluid connections. So 1-to-1.
Same tanks?
The tanks they're different tanks. They've got flight vehicle tanks, but as the engine interfaces, it's the same engine we're testing is the same engine they'll fly. And they'll be using cavitating Venturis.
Thank you. Good job.
Anything from the audience? Chad or William?
Well, first off, that was an awesome presentation. As I look through your trying to see the things I want to ask. Yeah, you go ahead.
Okay, so my question is on the annular gap for the pencil. So have you looked at you have a recirculation zone right there. So that's going to be a pretty high temp zone. But you're also flowing locked straight down the pencil. Have you looked at any thermal expansion effects on that clearance and maybe what resulting mass flow changes you're going to get? So that maybe your OF isn't quite what you thought.
Cameron, did you hear that? So yes, we have thought about that. No, you're good. So yeah, we've been having a lot of conversations about this. Professor Garrick is extremely upset with the tolerances we're asking for. Basically, we've realized that it's going to be very tough to get, and yeah, there is thermal expansion is one of the problems. Concentricity is going to be another one of the problems, and basically, yeah, we're just going to have to live with it. There is some thermal expansion effects. Mass flow rates of changing via like a 2 thou difference.
Do you have a resultant velocity vector for the propellants after they combine? So you have basically axial fuel flow, and I can't tell. It looks like your aux injectors are at an angle of some sort.
I'm pretty sure it's perfectly 90 degrees, and then we'll be getting a resultant coming out. I don't know exactly the angle, but there is a momentum ratio on one of our spreadsheets.
And then I remember the thing I was asking about. So I don't know if this is some research somewhere, if it's just something you thought of, but it's just something that I've never seen before. It looks like the nitrogen you're using for the purge is from your muscle supply.
Yeah, sure. Yeah.
So just wondering, have you considered, can your system handle that? While those are open, are you still going to have enough muscle pressure to deal with your muscle pressure stuff? And would you ever have a reason to want to have your purge pressures possibly higher or at a different pressure than your muscle pressure?
Yeah. So I combine them together, so it's one source. I like having that rather than having to have the air compressor running that we had to do before. If we do end up seeing a very large drop during purge where we can no longer actuate our pneumatic valves, I'll be throwing in accumulators near the purge valves, so hopefully that'll take the load off. And then I talked to Daniel Corey at Blue, and 100 people, we were purging at that pressure we set.
But yeah, definitely some in your facility checkouts as you're setting all this up, definitely just try to open your purges and dump
Yeah.
nitrogen and then try and actuate stuff at the same time that you're doing that.
We're going to be doing a lot of testing this year. We learned a lot from MP1, thank you. And yeah, so we'll be doing sequencing testing, a lot more of that too.
And then for the check valves going into your propellant tanks, is there going to be some type of checkouts on those or some type of replacement schedule just because we had problems with that on EP1 that you were there for?
Yeah, there's a lot of interesting ways to check out check valves. If we want to just stay consistent with that, or if we want to keep reusing the same component, we can do CV checkouts and check that, and back pressure tests. The really cool thing about our feed system that I really like, compared to at least MP1s, is that we have pneumatic isolation. So our upstream pressure is always going to be above 1,000 psi. And so effectively, you can't backfeed up from 550 psi up to 1,000 and then over to the other tank. Yeah, so it's a redundant feature there.
Is that still true on your shared purge lines between fuel and oxidizer?
So that is a more interesting location, and because of that, we're getting spring return pneumatic valves to make sure that they're always closed whenever we want. And the check valves there are at 10 psi cracking pressure too, just to give more.
One thing that I will say that I've never actually seen any of us do, including myself on this campus, is lay out a maintenance and inspection plan for every component and whatnot, because there are codes out there that tell you what you need to do and how often you need to check your relief valves and things like that, and many people won't know that.
I'll be working with Dr. Dangley to do it.
Okay.
He's been a great influence with that and making sure we're working on that.
Yeah, first system we've had that's actually going to last long enough to
Yep.